Can you see my screen?
Yes, ma'am.
Okay, so in last week's session, we learned about feature descriptors, right? Like how to compute Harris corner detector, shift descriptors, surf, and so on. So, why do you need to compute these features, or what are the applications of compute? I mean, designing features. If can anyone name a few?
Stitching images.
Okay, and so you guys do a lot of things with your phone, capture images, view it in different angles or and so on, right? So based on whatever you've seen in real life, so where are the applications for this? So yeah, as someone said, it is image matching and it can be used in image retrieval. So by image retrieval, we mean, so we have a reference image. Suppose I've taken a picture and I want to, like how Google Lens does it, right? So it basically searches for relevant images in its whole repository and then retrieves the most closest fetches for that, right? So that is image retrieval. So how does it do that? It like, I mean, obviously there are more sophisticated algorithms, but fundamentally what we expect an image retrieval algorithm to do is that I look for salient features in my reference image, and in my repository also, for each image I get those features and see for which image I can find the maximum number of matches where these salient features, like the shift descriptors which we compute, match, so that, and based on that we retrieve the closest image, right? So that is how image retrieval works. So fine, yeah, other than this, okay, I have a question, like, mm, in when we use shift descriptors, so suppose like this is a mountain range, right? So I have this as a reference image, say the left one is the reference image, and I want to retrieve other images. um, so suppose I don't care which exact, like the mountain range is. I just want to get a bunch of mountain looking images for to just retrieve some data so that I can train some models and so on. Do you think Swift will be able to retrieve these? Suppose you have taken a picture, you are looking for a particular type of bag which you came across somewhere when you were shopping, and you take a picture of that, and you are looking for something like that. Um, it need not be an exact identical one, but something of that style and so on. In such cases, do you think Swift can retrieve images from the data repository?
Maybe it can do to some extent.
Hmm.
If there is a larger variation, then maybe it cannot be.
Yeah, right. Like these are local descriptors which looks at the uh, let's say the intensity is gradients around a particular point, and based on that it tries to retrieve, right? That is how we define shift descriptors. but then that is not my use case, right? Like, I want a certain type of bag, but that doesn't mean they will be identical, right? Identical kind of features. But as a human, I know how a bag looks like. Like, there is no semantic information associated in SIFT, right? It's just local information, how the intensities are changing, the local gradients using which I describe the, I mean, get the SIFT descriptor, and I try to match those vectors. But in many applications, you would, suppose I want to classify images and so on, right? I have lots of cats and dogs, and I want to classify them as cats. So in that case, I can't have just one reference cat and try to match it with others. Would it work using SIFT? They can be of different colors, shapes, sizes, and so on, right? So in such cases, SIFT can't work most for most. So yeah, where, I mean, yeah, that's what. So when I don't care about all these, yeah, exactly, right? Like, all these are cars in this case. So, but then I don't want to, yeah, using SIFT, I won't really be able to match and get any matching points, right? It's not about how they have transformed. So SIFT can do retrieve something, or you can use it to image stitching when the scene is changed, or I have a particular book which I've taken, and that picture of a particular book, and then in a pile of I mean, and in a scene I want to match it to where that, like, check if that book exists, like if that template exists. In such case, it can do identical mapping, like based on the features identified. But in these kind of applications where I don't care about its local features, but it's more about the semantic information, like what is the structure of it and how do you define a car. It's not just based on color and having four wheels, right? So when I don't care about all such things, when I'm trying to understand what is there in the image rather than trying to match local features, that is where SIFT can't work, and we might need to describe something, like, get more sophisticated features. One such simple way of doing things is bag of words. So, what does bag of words mean? So, this was originally introduced in NLP, where you describe how you summarize statements. Suppose these are my samples. The first statement being, John likes to watch movies. Mary likes movies too. And then another line where it says Mary also likes to watch football games. Now, if I have to retrieve similar statements in a in a book or something, so I would want to describe features from this, and then using these features I would want to compare with my dictionary, right? Like, I have a dictionary, not dictionary, I mean, my database from which I want to retrieve. So how do we get features from this? So the elements of this the statement are basically the words, right? John likes to watch and so on. In yeah, as these are English words, so there is a vocabulary, right? Like, fixed number of words. So I can use that vocabulary, and based on that vocabulary, I just get a histogram of what word occurs with what frequency in a particular statement. Here, in the first statement, likes occurs twice, right? So the frequency of its occurrence is 2, and movies occurs twice here. That's all. So I can get a histogram representation for each statement, and I can use this as a feature. So inspired from this, so these are the elements of the statement, right? Like movies, watching, and then the person, the character in this case. In a similar sense, even in vision, we can think of an image to be formed from a bag of words, words referring to visual words. Suppose I want to describe a cat through bag of words. How do you, what are the elements that characterize cat? Right, it could be how the eyes are, the whiskers, ears, legs, and so on, right? So these are parts of the particular object which can be used to describe a particular class. So similar to how back of in NLP we can form a visual vocabulary of words from our database, as in like the training set, what is generally called as a training set. So if it is a phase, you can decompose them into different parts like this, and this becomes my vocabulary. And now when I have a new image, I can rather check if these kind of parts exist in that image, and retrieve based on that, retrieve or classify based on that. So any question? Okay. So yeah, given from my training data set, I can create a vocabulary, and when I have a test image, I can extract parts from that image and then compare it with uh, what I have in the vocabulary, and then get a histogram based on that, right? How many times this part occurs? Like how many times do you see an eye in the image, and the cycle see it, and so on, right? So based on how many times you see a part occur, so that becomes a characteristic of that particular image, and based on that you can classify. So for every image in my database, I mean, suppose I want to retrieve images, right, based on my the query image. So suppose I have k words which I have defined. So in this sense, how many words? This has 6 words, and then this has 5 words, and this has 6 words, right? So totally here we have 6 2s are 17 words, right? 17 words from this data set. In a similar sense, so suppose from an image database I have created 6 visual words, and now I have a new query which looks like this. So uh, so what does this vector here represent? There are six words in the vocabulary, and this is my query vector. So what do the elements in this refer to? Can anyone guess? So what is an image representation using this bag of words which we just discussed here?
Collection of features which we.
So I make a histogram out of it, right? So if there are 6 words, and in that image I see which word exists how many times. So the first word exists for one time, second and third word don't exist, then fourth, fifth, sixth word exist. So I have 100, 111, and in my second image I have only the second and fourth word in that image. So it is 010100. So based on what words exist, we have our bag of words representation, and this is what my query image looks like. That means it has the first and fourth word. So now we have an image database which is like this. For simplicity there are 5 images, and from given the query's bag of word representation, I want to retrieve its closest like the most similar image from this database. So how do I do that if these are my representations? Can someone tell which is the closest one for this query? it's written here, right? So based on this query, I check the similarity between the query and the image representation. When I match it with the first image in the database, so I see that both of them have the first and fourth word, right? So both one and so I have two common elements, so that's two. It's essentially dot product of both because these are binary vectors. And in the second case, there is only one common element, right? The fourth one. So the similarity score is 1. And in the third case, there is no common visual word, so the similarity score is 0. And in a similar sense, we get 1 and 1. So based on this, the closest vector which I would get is the first image, right? That would be the rank 1 retrieved image. Is that clear? Yeah, this is also a similar thing where if this is my query vector, 54, 67 and 72nd words are there. This is my repository. So I am seeing which all images in my dataset has this word 54. If it has, then I increase the counter by 1. So first I check my first visual word, then I check the second visual word and the third one which I have in my query image. Based on that, I get this scores, and then I rank them based on the similarity scores and retrieve them. But then in this case, all we are counting is, I mean, we are using to measure similarity is whether the visual word exists or not, right? uh, can we do any better than just counting whether a word exists in any sense? Like, can we use any different measure to get do better retrieval? So instead of using just how many times a word occurs in a particular in a particular image, rather than just using that, we can also measure how far the word in my query image is from from that in the vocabulary. So based on that, I can also get some distance measures, right, rather than just checking whether a word exists or not. So I can also get a vector, a distance for each visual word, which has obviously more information than just getting the histogram. So we can use these features instead of the scalar histograms which I get to compute the similarity or the distance. So So I'll now go back a bit to feature matching. So suppose, so what were we doing there? So suppose uh, we have two images, and then we want to map them, right? We like finding correspondences. So we would identify some certain key points here, and then identify the corresponding locations in this, and based on that we map this, right? And once we do this, you can do say image stitching and so on, right? But then in most of these can there is one other very nice, most very trending application of this, of identifying correspondence. Why do we need these kind of things? Where can it be used other than image stitching and classification, what we just discussed? So there are it's actually used, it would be used extensively in 3D representations. Like novel view synthesis. So the problem of novel. So have you guys heard about nerves? Not the nerf cartoon. Nerf models for 3D representations. Okay. Yeah, it's one of very recent model. So what novel view synthesis does is, so suppose I have captured image, as in, um, so there is a 3D scene, as in like any scene for that matter. So I have, can you spell that model? It is called NERF. Stands for neural radiance fields. It's used for novel view synthesis, and yeah. So the task is simple and very classic. In So there is this Google Street View and all, right? How many of you know what Google Street View means? Hi, you guys would have been. Okay. So what do we do in that? So basically we can see when we are walking through a lane, we can see a 3D visualization, or in the map based on at a certain location, we can view how it looks in 3D, right? But then how do we how is that 3D scenes actually synthesized? It's not possible that a person is moving a camera throughout from left to right and showing you what exists there, right? Practically, I mean, to if you have to visualize the whole world. So what happens in novel view synthesis, as in these applications, is, so we humans would have captured a few images in a particular scene, right? Like randomly I would have captured a few images. So all of these images, so I would have captured it in like say I have a camera, I look at it in this way, and the same scene I would look at it in a different way. I capture another image. So there could be like multiple camera views, and I capture the exact same scene but from different viewpoints. But if I have to actually see the whole 3D representation when I'm walking by, it yeah, yeah, that's exactly right. So I have to use the I mean, based on what is common across all these views, based on that I have to fill in for the other places, right? Like, so I have say five cameras, I mean five images captured from five different points. But then say I'm walking, this is how my path is, like I'm walking this way, and now I look around. So those five images, I mean, using those five images I should be able to get a 3D rendering of the whole scene, so that based on how my path is, I can see perceive it in that way. So this problem is called novel view synthesis, where we have certain images which are captured from few viewpoints, and from a new camera location, or from a new viewpoint, I want to see how the scene looks. Maybe I can show. Okay, this is the nerfed website. So basically, it shows if just from few images. So it shows if I move the camera like in a circular manner, how would the scene look? That is what this shows. Right, I'm moving the camera, like it's synthesized, as in this is not really captured by a camera, but the model's prediction. So here the camera's path is actually it's a circular motion. Like if I move camera in a circular motion, how would the scene look like? But obviously I wouldn't have
We present neural radiation.
okay, anyway, not that. Yeah. So this problem is called novel view synthesis. So in these kinds of applications, all these image feature matching methods would be used. So, but then these kind of transformation, to learn such models, we would have to model this in a 3D way, right? So we look into some geometric transforms, how geometric transforms are represented. So suppose yeah, I have like this is my original image, and then my so I do some transform, I apply some transform here, and then this is how it would look. So what have I done here?
Vertical.
Mirror image of the
Okay, not really me. Okay, what I intended was to shift it slightly towards the right. Okay, so I intend to translate this image, translate to a different origin. Now, so suppose this position was origin like point xy. It is now mapped to the point x prime y prime, and I want to know the mapping from x to y, like this to this. So I have my input would be xy, and I do something and I get x prime y prime. So whatever was there at the location xy is now at the location x prime y prime. So how can what is this operation T? Can I represent it in the form of a matrix? If so, what would that matrix be? Say I have moved horizontally, I shifted by Tx, and vertically I shifted by Ty. And don't be over smart. So if I have done this kind of translation, what would this matrix be? Can anyone fill in the values here? It's a 3 by 3 matrix, right?
Trans.
Or just tell me the relation between x and x prime, y and y prime, if I have done this kind of translation. So x prime would be x plus tx, right? I'm translating it by horizontally by x. And y prime would be y plus ty. I'm shifting it by distance dy. So given these, can you put these two equations into matrix form here? What should be these 9 values? Can someone write it in the matrix form? Tell me, read out the values. So what should the coefficient of x be? The coefficient of x goes in the first position here, right? The coefficient of x here is 1. So I have 1 here. What is the coefficient of y in my first equation? See, I have x, y and a scalar. Here also I have x, y I don't have, and I have a scalar. So this can be written as 1x prime plus, okay, what 1x plus 0y plus tx, and this can be written as 0x plus 1y plus ty. So now I just put these coefficients here. So from the first equation I have 1, 0 and tx. From the second equation I have 0, 1 and ty. What would the third one be? 1 is equal to 1, so I just have 1. So this is my translation matrix. Now instead of what is another common transform? Rotation, right? So something that is like this, I now rotate it by an angle theta. Now now becomes x prime y prime, and I have the matrix say R. Do any of you know what this, if I rotate, what would the coordinates become? What is the relation between this and this? So x prime is given by x cos theta minus y sin theta, and y prime is given by y sin theta plus y cos theta. So now given these two equations, what would the values in this matrix be? This at least you should be able to guess in the same way we did the above one, right? So based on that, based on looking at the coefficients, can you tell me what the values of this matrix are, the elements of this matrix are?
Cos theta minus sin theta and 0 for the first row.
Right, cos theta minus sin theta 0. Second row,
Sin theta cos theta and 0.
sin theta cos theta and 0. What about the third one?
0 0.
0 0 and 1. Right. Now suppose in the next case I want to do both rotation and translation. What would my matrix be now if I want to do both?
The product of the previous two translated T matrices.
The product of
The previous two matrices, transform matrices of T.
previous two matrices. Okay. What was it? 1 1 1. So what was this? Is this right?
excuse me, ma'am. In second column, in matrix 3 2, we will get dx sin theta plus dy cos theta.
Okay. That is fine, but then so how do we check whether this is doing what we want? The thing is having this third coordinate, okay, forgot the right way of explaining this. So by this equation, what I would get is x prime is becomes equal. Uh, x prime will become equal to x cos theta minus y sin theta plus tx cos theta minus ty sin theta, and y prime will be equal to x sin theta plus y cos theta plus tx sin theta plus ty cos theta. But what I actually want is actually, so just the rotation. If we, when I'm doing just rotation, I get this, right? This part. So I first want to rotate it and then translate it by tx. That time what I am actually expecting is this x cos theta minus y sin theta. So I've got the rotated coordinates and then I want to translate it by tx. So what I actually want to do is this. Y cos these are my rotated coordinates. So x prime is x rotated coordinates plus I want to translate it by tx. Similarly y prime is x y rotated coordinate plus ty. So I get this plus ty. So my transform to do rotation and translation is actually cos theta minus sin theta cos theta 0 0. It would be tx ty and 1. Now suppose I want to zoom in or zoom out this image. So I keep this rotation translation. While I do this rotation and I have an image. Say I want to first zoom in. Whatever was there in this space would now be enlarged, and then I rotate and translate by some. So from here to here I have some translation and then I have some rotation. So what are this equation what we have written is to do this, right? Going from this step to this step. But suppose I want to do this scaling. How do I do that? Or make it small. Zoom in or out. So can I modify this above equation so that I can incorporate this zooming in and out? So suppose the coordinate here earlier, say this was 0.5, 0.5 and this was 1 comma 1. Now I want this to be 1 comma 1 and this to be 2 comma 2. How would I do this? So whatever was at 0.5, 0.5 will now be at 1 comma 1, right? And whatever was at 1 comma 1 will now be at 2 comma 2. So my x prime from here to here would be 2x and y prime would be 2y. So to scale, what will be the so I would have x y 1. I would have 2 2 0 0 0 0 1, right? Whatever, like I can call it some scaling factor r. It could be zooming in or zooming out, 0.5x or 2x based on this.
Excuse me, ma'am.
Yeah.
Ma'am, here when we have zoomed in the image, we have the number of pixels. Suppose we have taken this 0.5 and 1 comma 1 as our extremities, and in the second case, the number of pixels in that region are increasing. Ma'am. So when we do 2 into something or some scaling factor, we are just keeping the number of pixels same, ma'am. So maybe I think this cannot be a valid transform or another understand.
Yeah, that obviously that is true. That whatever only the part of the image will now be in the resultant image, right? So many will go out of the range. So say this was 10 comma 10, now this will be 20 comma 20. But my pixel size will be same, so obviously it is zooming out. I can't see the whole image. So only the regions that fall within the image space will be there, and the rest will be discarded. That's what happens even in your phone, right? When you zoom in, you can't see all the pixels which you were originally seeing in. The mapping will be the same thing, but you will not be seeing the whole image. Does
Okay.
that make sense?
Yes.
Currently I'm not discussing those details. I'm just talking what the transform would be. But obviously, like logically, you would only look at the image space. So I would do this part. So I would do this part, and then what would I? So once I get all my, I mean, do this mapping, I would only keep my. I only keep x prime, y prime that are in the range like 0 comma 0 to 10 comma 10, which is my image space, right? I'll keep only that, and the rest will be discarded. But yeah, this is the geometric mapping, right? The transform. So I have done rotation, scaling, followed by scaling. I would want to do rotation. So in that case, what do I want? So I have got my so this is my second step, right? So I have got my rotated coordinates, which is x prime, y prime 1. Now I would do the normal rotation matrix, right? Cos theta minus sin theta 0 1 sin theta cos theta 0 0 1. Then what are my x prime, y prime? They are, or rather, rx and ry and 1. So cos theta minus sin theta 0 sin theta cos theta. So can I combine these two things in one matrix? So I can write this as 1 r r 1 0 0 0 0 and then xy 1, right? So now I can multiply both of these, r cos theta minus r sin theta, r sin theta, r cos theta 0 0 0 0 1. So this is my this is what I have for scaling plus rotation. So if I want to add translation to this, what would this matrix become? I would just add those, okay, translation scalars. So this will tx and this will be ty and 1. Yeah, one thing. So to do these two operations like scaling and rotation, I actually don't need this third element 1. If you see, right? Like this much suffices, right? If I have to do rotation, I can use a 2 cross 2 matrix to do it. But then I can't actually represent translation using a 2 cross 2 matrix, which is why this doesn't work. Multiplying these two matrices here.
Ma'am, but we first did rotation and then translation, ma'am, in the equations that you wrote. So, but when we are multiplying those matrices, we have multiplied in uh, first translation matrix on the right side and left side the rotation matrix. I think if we interchange it, it may work.
Yeah. What would it be if we interchange? Yeah, if we interchange, it will be different.
But the idea behind this is first we are applying a transformation and the output of that we are applying another. So that is equivalent of just multiplying the matrices.
Yeah, basically the meaning of this will change. What the translation that element is. Oh yeah, I understood why this is different, but I don't know if I'll be able to explain it to you. So
And in the previous,
if you switch this, would you get the correct matrix?
yes, ma'am, because we can see it in one more way. Like in the output that we got in like original multiplication that we have already done, in the output if we see and we group the terms in that, we can clearly see that it is a first translation. Here the cos theta terms if we combine, then x plus tx into cos theta. Similarly y terms. So it's first translation and then rotation. So it's clearly evident here. So if we reverse it, it will come. So I've just tried it. It's working now.
Yeah. Okay. There's one more. Anyway, so now we did scaling, rotation, and translation, right? There's one more thing where you can do shear, called shear, where you stretch the. So when we are zooming in or zooming out, now usually what we do is we zoom in both x and y direction by the same extent, right? Like by 2x. But suppose I want to zoom in the x direction with a different scale and the y direction in a different scale, then I can. Then that is called shear, which is represented by like say this is the shear in x direction, this is the shear in y direction, so it would be something like this. Anyway, so all these translations like these geometric transforms like translation, rotation, uh, shear, scaling, all these are called affine transforms. And any affine transform, say even if we don't know what exactly the transform means, as in, so these are, I'm defining this is the rotation and these are the matrices, right? But in general, when we have like an image, like corresponding key points, I wouldn't exactly know what all is happening, translation, rotation, shear, scaling, right? Like to decompose them. So all kinds of any kind of geometric transform can usually be represented in this way, where your where it has 6 degrees of freedom. So any affine transform matrix can be represented like this in when I'm transforming, doing a transform in a 2D space. So when we don't know what exactly is happening, like all these decompositions, like different things happening, I usually would have point to point correspondences in the image, like how we use shift key points to match them, right? So based on that, I would want to estimate what this matrix is. So yeah, like this is a system of equations, right? Which is of the form ax equal to b. So this, so I would have, so x, yeah, so my, so x and b, these are the point to point correspondences which I have. So given some point to point correspondences, I would want to estimate what the transform is, geometric transform is. So how do you solve this? How do you estimate this here? If you have these point to point correspondences. So I can use least squares method to estimate here. So what is least square? And do you guys know what least squares method is? So I want to get the best a for which my ax minus b, the error, like if I define this as the error ax minus b, the norm of ax minus b, so I want to minimize this error to get my best solution, right? So what is the best so suppose I have a lot of say this is how my data looks like. So and I want to fit a line here. So how many points do I need to fit a line? So all these are actually lines only, right? So what is the equation of a line? How many data points? So here what do we say? We have these correspondences, right? So I have all these points which is x and y, right? B as in what? Fine, I can write this as y, or ax is equal to, yeah, ax is equal to y. So I have all these points, say x1, y1, x2, y2, and so on, right? Some x and yn. So I have these point to point correspondences. Now I want to fit a line to it. So what is my how do we write line? Y is equal to mx plus c represents a line, right? So how many data points would I need to fit a line?
2 data.
2 points, right? So what do we do here? If I want to fit a line, what I would do is actually, so I take my points, say, so I have x1, y1, and so on, right? If my input is yeah, say for x1, if so I want to estimate, I want to so the model parameters are m and c. I want to estimate the best m and c that fit this line, right? So if I have x1, so I know x1, I know all of this. What would y, and I will estimate y1 cap, what y could be. If I use this model, what would the y be for this particular point? So y1 cap would be mx1 plus c. Similarly, y2 cap would be mx2 plus c, and so on, right? So I have n data points, I have n estimates plus c. What I want to do is actually minimize the error between this estimated point and the, so I know the real data points, right? Real true data points like the x1 and its so what I want to do is whatever yk minus its estimate, I would minimize this to estimate by my best parameters m and c that would minimize this error. This is called least square solution. This is called least square error. So you can actually write this as a data matrix and then solve for m and c. So if I have to put them in a vector form, so I take y, this will be all my true data points y1 to yn, and all my estimates would be of the form mx1 plus c, mx2 plus c, and so on, right? Which I can x2 xn, and I have 1 here. So this is my system of equations, and I will solve for this. So I know this and this known from the point correspondences. So is this clear how this least square least squares is formulated in this case?
Yes.
So this will all work fine when my data looks very structured and there is one line which I can cleanly estimate given the data. But many cases, when you have a lot of outliers or noisy data, it is not easy to estimate this line that well. In such cases, there is a robust version of this which is called as RANSAC. So I'll go over that algorithm. I'll just go over the slides for that. You can see the screen, right?
Yes, sir.
Yeah, so usually if my data is very clean, then I can solve the simple problem and get my weights. But then suppose my data looks so haywire like this, or if I have a few outliers, right? In these cases, using simple least square, all of these points which are probably erroneous also contribute to my error, right? Some cases, this is a good example here. So I have uh, so here, this in this case, the model fits nicely and I get this. But suppose I have just one outlier, which is this point here. Now this point would actually contribute a huge error, right? The original line is somewhere like this, but then I have all these points would give small error, but this point would give very huge error. So the model will try to fit, the weights will try to adjust such that it can fit this point as well. It doesn't know that it is an outlier. So by doing that, what happens is this would be the model parameters that are estimated, like the slope and this. But then this is obviously not a good fit, right? I would want to get a line which fits for most of the data points, not the one that fits the outliers, right? So I would rather want to ignore this and just use these points to get a line. Does that make sense? Hello?
Yes, sir.
Okay. This is a very simple example here, but even when training like large deep models, right, if there are any noisy points, so most of these data sets would be human annotated, right, but there can be errors induced by humans. So suppose a person has wrongly labeled say a cat as a dog, and then that would be an outlier point like this, because it it originally is a cat, but I am trying to match the feature of that to a dog, right? So while doing that, it would actually induce very huge loss, and the model, if the model tries to fit that, then I would not be learning the best classifier possible. So it is actually important to handle outliers or try to ignore them I mean, like, there are different ways which people do that, but it is a very important problem how to handle outliers when you're learning a model. So yeah, so when I have a data which looks like this, even in this case I know this is a good fit, right, a line like this. So how do we do that? How do we ignore outliers and try to get the best fit possible? So for that they propose there's this method called the ransack. So what they do in ransack is they just pick, so from the whole, say I have 100 points, I randomly pick 2 points. Say in this case I have picked these 2 points, it's completely random. So as I just want to fit a line, right, I will fit a line. How would the line be? It will pass through these 2 points, right? This is how the line would be. But then once I uh, here, because it's two-dimensional data, we can look at it and say it is not a good fit, right? It doesn't fit most of the other points. So how do I evaluate whether it is a good fit? For that I take a margin around this line, like a small margin around this line, and then see how many data points fall within that margin. So this is how we draw a margin around this, and then count the inlier points. Inliers are the ones which lie within this margin. So all these points here, right, which we can see 1, 2, 3, 4, 5, 6.
Excuse me, ma'am.
Yeah.
The screen is not visible.
Oh. Can you see now?
Yes, ma'am.
Okay. So where did you lose me? Did you see the previous one? So I randomly pick 2 points from the whole data set and I fit a line, and I impose a small margin around it, and then check how many inliers are present. That is, how many points are present within these two lines. So the idea basically is, so if a line is a good fit, I take a margin around it. There should be a lot of points within that margin. Like for a good fit line, if I take like the best line which we can see in this case, if I take a line around this and take this margin and see, there would be a lot of points in that around the line estimated, right? So that is what we are trying to look for. So we count the number of inlayers. So these green points, right, are the inlayers which lie within the margin. So we have 1, 2, 3, 4, 5, 6 inlayers. So I have one line, and so I keep storing these parameters and the corresponding inlayers. So I have 6 inlayers. So then I randomly pick another 2 points, say these 2 points, and then I fit a line, and then I count the inliers. So we keep randomly sampling 2 points in this case, fit a model, see how many inliers are present, and keep updating the best hypothesis which we've seen. So compared to the previous 2 points, I know this is a better fit, right? Like this is more closer to my best hypothesis than, yeah, so this is a better model than the previous one, right? So I update and store this as the best model I've seen so far. Then I again sample another 2 points, do the same thing, calculate inliers. So the number of inliers should be maximum, and that is the best fit. As in, you keep a threshold to search for the number of inliers, and once you reach that threshold, you assume that okay, I have now converged and got a good fit. So you keep repeating this, like, so this is again a bad fit, right? So we don't keep we keep the previous model parameters itself in such case. So you keep doing this, and then based on the number of inliers, you decide to stop. So to summarize, yeah, so we have the data points, and n is the minimum number of samples to fit the model. That is, if I have to fit a line, I need 2 data points, right? So so S is the score, that is the number of inliers in this case. So I keep repeating that. I randomly sample n samples, that is in this case 2. But if I have to fit a plane in a 3D space, then I would have to sample 3 points randomly. So we draw n samples randomly from the whole data set and then fit a model, get its parameters, then check is it consistent with the hypothesis. That is, I compute the scores like the inlayers, the number of inlayers. If the number of inlayers is greater than some threshold, then I update my parameters. As in, I say till now this is my best which I have achieved, so I keep these parameters now. But then, the limitations are that we have to define the inlier ratio and so on. So I will go over the code for this ransack algorithm. So that was a simple case, right? What we showed, that is 2D data points I have, but in reality I might have data in some high dimensional feature space, that is in an n dimensional space, and I want to fit a polynomial like this. No, as in, if I have to fit a line, so I can search to fit any kind of curve, right? So suppose I want to fit a polynomial in an n dimensional space. This is how my equation would be. So these are my point correspondence, right? X and y, x1 y1 x2 y2 and so on. So these are my data points x1 y1, and I want to fit a polynomial. So because I want to fit a polynomial, this is how my system of equations would be. So what am I doing? I am just substituting x1 y1 in this polynomial equation, right, and writing them in matrix form. So y would be some linear combination of the b0 plus b1 x1 plus b2 x1 square and so on, right? And this is the error term. What is my objective? I want to minimize this error, right? So that is the linear least squares objective, where I'm trying to actually minimize this error. That is why we get this norm of y minus x beta in this case norm. So, and the least square solution for this system of equations is actually in this form. So in ransack we actually build over this, right? We keep sampling data points, get these beta parameters, then see how many inlayers are there and so on. So what we are defining here is, this is a class to solve this ransack. One is the order of the polynomial, and
My screen is empty.
oh, I don't know why is this happening. So we define the number of iterations, the order of the polynomial and so on. So the prediction function is where I give the beta. So once I have the beta parameters, we pass it through this numpy function, which basically returns me this. So if I give beta and if I give x, then I get back y. So this numpy is 1D polynomial we have, right? So using this function we can get what the output is. So this is my equation, and I pass x through this polynomial and I get my estimate y. So when we are solving, one thing is, here we initialize a random seed. So the best error until now, it's initialized to minus infinity. It's initialized to infinity, and the number of iterations and threshold is defined here. So now I go into this while loop. So I search for certain number. I do this search for certain number of iterations, where first I just sample n points. So here n is equal to 2. N would be 2, right? Where have they defined n? Okay, which will pass n, I think, later. Anyway, because this is 2D data, so n will be 2. uh, so from the whole of x, I sample 2 data points and I get the flags for this, as in it returns me which those 2 data points are. So this will be a boolean vector. So I use those 2 points only, x and y, and this is the order of the polynomial which I am trying to fit. And I so this returns the beta that would fit these 2 points, I mean whatever is sampled here. So once we get that, then we pass the inputs, all the data points through the predict function. So we are setting this beta, right? So the prediction function would actually use that beta and we get the estimates. So we do this and then we calculate the error. This is the absolute error between the true point and what the model has predicted. So this is my error. Then we identify the inliers within the threshold. So error is actually giving me the delta which is from the line, right? So if I set some small threshold, what is the threshold they set? Yeah, some heuristic they've used here, but anyway, so you use a threshold, and if that error is lesser than threshold, then we call it as an inlier point. So and we see how many inliers are there. So you keep a measure of how many inliers you have until that point. So this term close points will keep track of the most inliers until that time, that search, and this is what I have at the current estimate. Yeah, so the condition used here is if the number of inliers now is greater than the previous one, as in if that says it is a better fit, right? Or my current error is lesser than the best error whatever estimated till now, then I update this, the close points as in the number of inliers to the current one, the best error to this, and best coordinate. So this is my okay, what is yeah, which were those data points which were used to compute that model. Okay, yeah, this is I think like some adaptive way to I mean decide when you want to stop this algorithm. But anyway, without that as well it should work. So I keep doing this. So once these conditions are met, yeah, once you reach this best error, right? If the model error is less than, when would it fail? Yeah, once so you have found your best line, so later after that, whatever the number of inliers you count are always lesser than your close points, then you would not go into this and you come out here, right? Or reach your maximum iterations, and in such case you would have identified what your best parameters are, and then I find my beta. So and it would return the best parameters and error. So yeah, this is some 2D data set, and uh, so because it is 2D, we are this 2 refers to the order, or I mean the can you mute yourself, Revati? Yeah. So 2 is defines the order of the polynomial. And then we solve it by passing our data points and we get the best beta, which is a second order polynomial here. And yeah, for this line, the blue points show the inliers and the green ones show the outliers. Yeah, and also we might not always know what the best order is, right? In such cases, you would have to search through this, as in try different order polynomials, like passing through them, and then see for which order it gives the least error. So suppose I try to fit a line here. This is how the line would look like, right? So this line would have more error than using a second order polynomial. For order. Okay, this will overwrite, I think, but so okay, this is the line estimated, and this is the second order polynomial. Oh no, it starts from 0. Yeah, should have started from 1. Yeah, so this is a line. This is how second order curve is, third order, fourth order. Yeah, so we can see what is the error for each of this, right? So yeah, we can see that the error is least for the fourth order polynomial here, right? But then so what do you expect? When I'm increasing the order, I'm increasing the complexity, right? And the number of coefficients increase, so I'm increasing the complexity of the curve. Do you think this increase, if I increase complexity, I will almost surely always get a better model, right? I'll try to minimize errors, I'll make it more curvy, whatever, and the errors would minimize. But is that a good thing always, do you think?
No.
Why no?
We have to have that much amount of patience needed for our task. It is going more complex for us, but unnecessarily we require more computation.
Unnecessarily what? I didn't get
More
it.
computational.
For no, I mean, assume, don't think about computation now. I just want to get the best model possible. Will I always get a better model by using more complex ones? So maybe let's see if I can put 10 here. So what do you see here? So your error has gone down, right? From say fine, second one is 0.21, 0.23, 0.19. Then it actually started increasing. 0.25, 0.26, 0.25, 0.25, 0.7, right? It actually started increasing. Why did it increase? You can see the curves, right? If I'm increasing the polynomial order, then I can get more intricate lines, not line, like obviously curves. But this doesn't really look like a good fit, right? So here in this case, I'm seeing only this scale, say a point in the scale range of -1. So suppose I also have data points which goes a little out of this range, then it might completely like shoot up, right? Which my data can't handle. Like I might not have data in that space at all. So this is called something called overfitting. It will be discussed in a few lectures. It's a common phenomenon in neural networks as well. When you try to make the models more complex, you might fit your training data well, but then when you are testing it, it might not actually do well because it would have overfit on the training data. So it will try to make least error for your training samples, whatever is sampled at that time, but then at the end, when I want to generalize and test across lots of test samples, it might not be a good fit. So unnecessarily complex models, more than what the data is required, it should not be complex actually. So it depends on the data. So this, the line is too simple for this, right? It obviously doesn't fit well. But from second order, it looks fairly good for us. So this is not a good fit, we can say, by looking at it. So this is called underfitting. Here the model is not complex enough for the data. So this is called underfitting. And yeah, like order 2, 3, 4 look fine. But then again, like higher orders uh, are complex for this data, which is unnecessary, and it's called as overfitting. I actually wanted to discuss that Huff transform also, but there's not so much time. So we saw how to fit a line or a curve given data points, right? So suppose I want to like fit multiple lines together, or even line detection in an image. Suppose I have a given image and I want to detect all the lines in the image, lines or any parametric curve like a circle or a polygon or so on, right? Anything which you can define via parameters. So a particular shape basically. If I want to detect, like say there are coins in an image, I want to count how many coins are there in the image. That means I want to detect how many circles are there in the image, right? If I simply translate it. So I have a coin image and I do some edge detection and get uh, get circles from it. So I want to use that image and detect how many coins are there in it, right? So if I have an algorithm to detect circles, then I can count them, right? How many circles are there in a similar sense. So this Hough transform is was originally designed for proposed for lines, but then there was a generalized version called generalized Hough transform, which is generalized for any curve. So how do we detect if there are lines existing in an image? So what happens is so how do we represent a line as in the form y is equal to mx plus c, right? And what do we want to do? We want to get the line. So the line is parameterized by these two values, right? M and c. M is the slope and c is the y-intercept. So we want to identify what m and c are. If you identify what m and c are, then we know what the line is. So to search for these parameters, what we do is we change this equation and rearrange it to write it in this form where c is equal to minus x as the coefficient m plus y. So we are going from the space xy, the coordinate space, to the parameter space. Here the parameters are m and c. Basically your like whatever was in the I'm going from the xy space to c and m space. So if I have a point xi yi which goes through a particular line, then it will satisfy this equation as well, right? C is equal to minus xi m plus yi. So this can be thought of as a line in the parameter space. So this is a line in the Cartesian coordinates. This is a line in the parameter space. So every point in my parameter space is actually a line in I mean every point like every coordinate, if I take a random point in the coordinate space of c and m, it actually refers to a line in my original space. Did you understand that?
Sorry, I cannot see the screen
Oh god.
presented. Is that only me or oh,
Yeah.
I can see now.
Okay. Yeah, I don't know why that keeps happening. So any line in my Cartesian coordinate space, xy space, is actually a point in the parameter space. And any line in the parameter space turns out to be a point in my Cartesian space. So another way to represent a line is by in the polar form, right? So why is this done? I mean, why we do this is that, so when I'm going from the line space to the I mean the parameter space. So for so for the vertical lines, the slope is unbounded, right? Which I can't represent in the parameter space. So that is why polar parameterization used. Anyway, even here we have only two parameters, right? But one is the distance from the origin and the other is the angle. So we have two parameters, rho and theta. So we go from the coordinate space to the parameter. So this is my coordinate space and this is my parameter space. So when I take a point in my coordinate space x1, there can be any like infinite number of lines that pass through the point, right? Horizontal, vertical, I can draw any number of lines that pass through this point. So if I for each of that line, so I mean this point votes to all of those lines which are which can possibly pass through this point. So this point I get a corresponding what parameter which is here, and for this line I again identify what are the parameters of this line, and I plot them here. Similarly for this line, and I keep plotting what these lines, all these lines that correspond to x1, I plot them in the parameter space. So once you yeah. So similarly I can pick another point, and for that also I keep plotting the corresponding parameters in the parameter space. So if I want to find the parameters of the line that passes through x1 and y1, it will actually be the intersection of these curves in the parameter space. So the blue one here represents all the parameters, I mean the parameters of all the lines that pass through x1, like this in all directions, and the red line represents the the parameters of all the lines that can pass through x2, which is like this. But there is only one line that can pass through both x1 and x2, right? So the point where it intersects in this parameter space, this point would actually be the line that will, the value of theta and r that represents the line connecting x1 and x2. So if we have an image like this, like an edge image, so I have these lines here, right? 1 2 3, there are 4 lines here. So what is done is
Ma'am, I'm unable to see the screen again. Okay, what's happening? Hello? Okay, now it's there. Thank you.
so if we have an image like this, an edge detected image already, and we want to identify these lines, so what we do is we go through each edge point like these edges, and then vote for them in the parameter space. So there are 4 lines, so there would be like 4 different peaks in the parameter space, and it will look something like this in the parameter space, that is the r and theta space. And then we see those points which have the maximum number of votes. We can see 4 distinctive points here, right, which actually corresponds to the line parameters of these 4 lines here. So that is how you can detect, or you threshold this accumulator array which is in the parameter space, and we get these 4 points. So these 4 points correspond to 4. So and then you use those parameters r and theta and plot the lines. This is how the lines would look like. So from this image we have actually identified the lines. So the same logic can actually be used for different any kind of curve as well. So in this case the parameters were that r and theta, right? Similarly we can do the same logic to find circles. So what are the parameters in the circle? So xy is the coordinate, so the circle is defined by its center x0 y0 and its radius, right? So the parameter space becomes x naught, y naught, and r. So there are three parameters, and so you would have a 3D array, 3D accumulator array with which searches for the x naught, y naught, and r. So if you have this image, you can use canny edge detector to get these circles, right? And then you do the Huff transform to find these circles. So you look at the so the logic is actually the same. So instead of the 2D array here, you would actually have a 3D array corresponding to the three parameters x naught, y naught, and r. And in that 3D array, you do identify the local maxima, and those points in the 3D array will give us these points, like I mean the x naught, y naught, and r. So if you use that x naught, y naught, and r identified there and draw them, you would have identified the circles. So if you have any kind of parameter model, any shape for that matter, not just circle, that is what they show in the next example, I think. Yeah, like if you have a model image which is like a car here, so and if you can represent this in a parametric form, then you can like template match. So this is sort of like template matching in the parameter space. So you can do that matching vote in the accumulator array and identify yeah, so this is what is called as generalized Huff transform. So yeah, so when you know a particular exact shape, how a model would look like, you can define, can somehow, if you can somehow define it in a parametric form, then you can search for it in any any image. Okay, then that's pretty much what I wanted to cover. Were you guys able to follow me? I mean, I understand some parts were not explained that well. If you have any feedback or suggestions, you can tell me. Oh, what did you have in this week's lectures? Feature matching. Deep learning introduction. Okay. Oh, I saw the content from here and I did this. So this whole content was not there, is it? Like, was feature matching at least there?
Let us start with the last week. After the last week's content today, this week it was started from psychologics, neural perceptron, and things like that.
Which one?
Perceptron and perceptron learning algorithm, and then feed-forward networks.
Okay. Oh, I saw it from this, like where the notebooks are posted, right? Based on that, I did this.
In the GitHub, it was not updated. the lecture.
Okay, okay. Yeah, I think the course was restructured where they removed that part. Okay, I'll cover those in the next week. Assignment question seems to be tough.
Is it possible to share the notebook that we were talking about?
Yeah. So the notebooks are all here actually. The get this in this GitHub site it's there. So based I saw this and I did this content actually. But yeah, like from next week I'll do the deep learning part. Okay then, thank you everyone.